Hey guys, this video is about Q, the reaction quotient. So let's first talk about K, the equilibrium constant, capital K. Um, if the value for K is greater than 1, what we say is the equilibrium lies on the right, and if the value of K is less than 1, we say the equilibrium lies on the left. And what we mean by this is because remember, the equilibrium expression K is equal to the concentrations of the products, the right-hand side of the equation, raised to the powers of their coefficients, divided by the concentrations of the reactants, the left-hand side of the equation, raised to the powers of their coefficients. So if K is greater than 1, basically that means that we have more products, the right-hand side, than we do reactants, or the product, or when we plug into the expression, the concentrations raised to the powers in the numerator is greater than the denominator. And so that's what we mean by the equilibrium lies on the right. Likewise, if K is less than 1, the numerator is smaller than the denominator, and basically we have more reactants at equilibrium than products. Likewise, if the value for K is very large, what that means for us is that basically that reaction, we say, goes to completion. In other words, while if we could see the atoms and molecules at the microscopic level, we would see some moving back and forth in that dynamic equilibrium model. But for a practical matter, if K is large enough, the amount of products that go back and reform reactants is so small that either we can't measure it or it's lost in the sig fig somewhere. So for us, that's basically a single arrow. Likewise, a very small K means that because the K is so small, we have so few products, almost basically all reactants. What we say is that reaction does not occur to any appreciable extent. Now, we're going to see in a later module, we're going to see the tables and tables of what are called KSPs, solubility products, the equilibrium constant for dissolving an ionic compound in water. And you're going to see some values in there that are huge, 10 to the 80th and bigger. It's huge. And really, really small, 10 to the minus 80th. It's really small. And so sometimes it's useful to have that number and to do some calculations if we are in a situation where that minute amount that's going to be in equilibrium matters to us. But most of the time, in everyday lab life, it doesn't matter. Big K, completion, small k, doesn't occur. Now, let's compare the two Ks, tale of two Ks. Now, capital K is the equilibrium constant, the equilibrium expression. Now, that says nothing at all about how fast a reaction will get to equilibrium, just that when the reaction does get to equilibrium, the concentrations of the products and the reactants will be such that they satisfy the equilibrium expression. On the other hand, little k, lowercase k, is the rate constant. That tells us how fast the reaction will get to equilibrium. Now we can see where these come from in their relationship if we look at a reaction coordinate diagram. Remember, in a reaction coordinate diagram, we have the energy of the system on the y-axis and the reaction progress on the x-axis. Basically, you can think about the x-axis as being time, where at x equals 0, we have only reactants they have not started to react at. That's before anything happens. And at some time later on over here, we have all products. And so the value of the rate constant, how fast this reaction comes to equilibrium, depends upon the size of the activation energy. Remember, the activation energy is the difference in energy between the energy of the reactants and the highest peak they have to overcome, the activation barrier, we call that. Remember the Arrhenius equation. That gives us the relationship, the mathematical relationship between the rate constant, little k, and the activation energy. It's an exponential relationship. So the higher the activation barrier, the higher the activation energy, the slower that reaction is going to happen at a given temperature. And the lower the activation barrier, the lower the activation energy, the faster that reaction will occur at a given temperature. Now, the equilibrium constant, capital K, the magnitude of it depends upon the difference in energy of the products and the reactants. And that's this difference in energy here, the energy of the reactants, the energy of the products here. I happen to draw an exothermic process. It works just the same for an endothermic process where the energies of the products is higher than the energies of the reactants. So little k depends on activation energy. Big K depends upon the difference in energy of the reactants and the products. Delta E or delta H. All right, Q, the reaction quotient. So looking at our generic equilibrium reaction, AA plus BB in equilibrium with CC and DD, if we write down the equilibrium expression, which we know how to do now, it's just the concentrations of each of the products, C and D, raised to the powers of their coefficients, little c and little d, over the same thing for the reactants A and B. And these concentrations, guys, these are the concentrations at equilibrium. That's important to remember. Now, if we're not at equilibrium, let's say we just mix everything together and don't give it a chance to come to equilibrium, same thing, we put those values in, and the value we get is called Q, the reaction quotient. And Q changes all the time. So, usually we write the initial concentrations in Q. So initial, that's what the sub-zeros mean. So it looks a lot like the equilibrium expression, except it's those same values when its system's not at equilibrium. Now, once the value of Q is equal to the value of K, that's how we know the system is at equilibrium. If the value of Q is equal to the value of K, it's at equilibrium. On the other hand, if the value of Q is bigger than the value of K, what's going to happen is, well, first of all, that system will come to equilibrium eventually. How fast? We don't know. That depends upon the rate constant, little k, but it will. And what's going to happen is if the value of Q, guys, is bigger than the value of K, we know that what's going to happen is the equilibrium is going to shift to the left, to the reactant side in order to achieve equilibrium. Here's why. So if Q is bigger than K, that means that the numerator in Q is too big and the denominator in Q is too small compared to their values in K. And so because the numerator gives the concentrations of the products raised to their powers, that means we have too much products. The concentrations of the products is too high and the concentrations of the reactants is too low because these values are too small. And so what happens is some of the products reform reactants until we take some of the C and D away, make more A and B, until we get Q to equal K, and then it's at equilibrium. Likewise, if the value of Q is less than K, now the numerator is too small, denominator is too big, and so what happens is because now we don't have enough products, equilibrium is going to shift to the right until we achieve equilibrium, until Q equals K. So that's actually a really, really useful thing to know and to be able to use. So here's an example. So we have this system, this reaction, this equilibrium reaction, and we're given the value of K, 2.2, and we mix all these reactants and products together. We put everything in the, just everything, right? And these are their initial concentrations. So ethanoic acid, ethanol, diethyl ether, and no, that's an ester, sorry, and water. Notice, okay, usually when we have water as a reactant or product, we don't write it in the equilibrium expression because its concentration doesn't change. It's a liquid. Here, it's not the solvent. It's a solute, and its concentration will change, so we have to include it. So a question, guys, is which way is this system going to shift in order to achieve equilibrium, and why? So go ahead and figure that out. So basically, find the value of Q compared to K, and then see what happens. When you get an answer, come on back. Welcome back, guys. So there's our equilibrium reaction. There's our K. There's our initial concentrations. All we do is plug into the reaction quotient Q. Okay, the values that their initial values, get the value, and it ends up, I got 0.40, I think. That's because that value is less than K. The equilibrium will shift to the right, and we'll make more products and take away some of those reactants. That's all there is to that, guys.